Okay, somebody started recording. I allowed like two people to do it, and then like I can't allow somebody else to record. Yeah, I gave permission to Yusuf and William, but for some reason I can't give it to Huyin Win or Win. Anyway, um, as long as Yusuf and William are willing to share with the rest of the class, or upload it later, I think we're good to go. Okay. What the heck? Let's do this. Okay. Binary representation. How do you make a wire or a semiconductor hold a number when the only states are off and on? Uh, hmm. So, as you may have guessed from the name, binary means there's two numbers in the thing, 0 and 1, off and on. So, with decimal, you have 10 numbers. So when you run out of symbols to count with, what do? Well, you say you have two symbols instead of one symbol and continue counting normally. What do you do when you run out of that again? Well, you add another symbol and so on and so forth. Same idea with binary. Ran out of symbols, okay. Ran out of symbols, okay. And so on. Something you'll note is, let's see, each one of these numbers corresponds to a power of 2. So in this case, it'd be 2 to the 0 for 1, 2 to the first, or 2 to the first power for 2, 2 to the second power for 4, 2 to the third power for 8, and so on. Also so happens that the calculator in Windows has a programmer version or mode, and you can see in this case let's go with 1. Yeah, that's the same across everything. Another 1 that went from 1 to 3. Well, why? Because just like you'd add two numbers together, so what the heck? For the class, who wants to guess what this number, who wants to guess what 0, 1 plus 1, 0 is? 1, 1, correct. So And I think you get the general idea of how do I add these things together. So like 1 plus 1 plus 1 plus 1, or 4 ones is 1 plus 2 plus 4 plus 8. So 15. And of course, once you go past that, well, you ran out of room to put it, so it flips over to the next number up. Oh yes. So 15 plus 1 would be 16. And you can see 15 was all ones there. You add 1, moves over there, and so on and so forth. So this is very nice. So let's say you have a byte. You have all those to play with. So you should be able to go up to 255 if you just care about positive numbers. But what if you need negative numbers? Wow, how weird. That final bit turned it from very large positive number to very small negative number. So that went from 0 to a very large negative number immediately. So an early version of, I don't know if it was earlier, if it was around a long time. Short version was, well, we have all these numbers. How do we get negative numbers? Well, obviously, if you have positive number and negative number, you could just map that to a bit. So whatever the leftmost bit would be a negative number, or it'd be, if it was a 0 on the leftmost bit, be positive. If it was 1 on the leftmost bit, it'd be negative. Short, sweet, to the point, very straightforward. Small problem that happens is, well, what if it's a 0? Well, then you get positive 0 and negative 0. As you can expect, when you're fighting and scraping for every last ounce of information you can grab, this is unacceptable. So what was done? So actually, like you can see here, bytes, words, double words, quad words, etc. So unsigned, you have 0 to 255. If you have the signed range, it's negative 128 to positive 127. Well, how do you get that? Or what's the difference between the two? Well, instead of using the leftmost bit as a positive or negative sign, just have it be the absolute biggest negative number you can have, and have all the other bits remain positive numbers as they were before. And then just add them all together like you would normally. Like, or as mentioned, 1 plus 2 plus 5 or 4 plus 8 is 15. And you get that just by adding all the digits or all the powers of 2 together. So instead you have the biggest power of 2, but make it a negative, and then you can have a range from negative, whatever the number is, to positive, almost the same amount, minus 1. I think there's a specific, like, and whatever. Oh, yes. And to double check this sort of thing, so using bits normally, just add them up normally. That makes sense. But how do you get a, but adding it up manually takes a long time. How do you get the, how do you get a given value and then find its negative without working it out by hand? You use something called the 2's complement. Essentially, the 2's complement is just, or the 1 complement is take the numbers of that thing and flip them. So let's go with 4, because I don't want to bother with the whole, well, I'm gonna have to bother with the whole shebang anyway. Let's go with the 64-bit. So the 1's complement of that is just, well, flip the bits. Every 0 becomes a 1, every 1 becomes a 0. And then you add 1. Does anybody want to give a guess as to how you add with binary things? So in an anticlimax, you add binary numbers just like you would normally. You would add decimal numbers. So in this case, right-hand most column, 1 plus 1. Well, that's a 10. But you run out of space to put it, so you carry the 1. 1 plus 0 is 1. Then you go 1 plus 0 is 1. And yeah, I see the correct answer in chat. And again, that's what this is kind of useful for. That's mostly as a haha funny trick thing. But that's how you add things. If you want to subtract things, well, how do you think you subtract things? Again, same thing as, yeah. Correct, it is just like that. What happens if let's go with an example we already know the solution to. 6 minus 1. Well, there's nothing we can subtract here, so what do we do? Yep, again, nothing new under the sun here. This one gets borrowed, or like you'd, I mean, just like 10 minus 1 in decimal, where you get 0.9, you borrow 1 from the next column over, you subtract it, and then you hit the highest symbol on the other thing around. So, like, to use an example, in hex, if you have 16 in hex, you subtract 1, you end up with F, which is the highest symbol on the base 16 thing. I'd actually kind of call it like number A, number B, number C, etc. But so anyways, to find the positive version, or to find the negative version of a positive number using the complement, it's okay. You add 1 to it. So 1 plus 1, 0, carry the 1. 1 plus 1 is 0. Carry the 1 again. 1 plus 1, 10. Carry the 1 again. 1 plus 1. You can see where this is going. Up till we hit this point, in which case we finally hit a 1, and then there's nothing to add here. So it's that. And hey, look, would you look at that? That's just with 1 bit though, so I mean, the other way to do it would be, I could just do it with, what's the negative 1? Well, then, actually, let's put it to the chat. Teehee. What is the bit representation of a negative 1 in this case? Also, don't be shy. If you want to unmute, you can. Correct. 2:30. Okay, I have plenty of time. Right example. Yeah. And you can see this in chapter 3 of your book. Word example, unsigned and signed addition. The reason you'd care about signed versus unsigned when most of the things you've touched have always been probably pretty high level languages is, what's the best way to put this? So some things can only be positive, or they have some vector and they have a direction and a speed, and both of those can only be positive sort of things, which would make your things much faster, or like you'd have twice the headroom to reach around and calculate with. With the negative ones, well, you have half the space, or rather, you have the same amount of space, but half of it is underground, so to speak, below sea level, or however you'd like to call it. Let's see. Oh yes, floating point representation. So binary. It's weird, but it's not alien to regular counting sensibilities. You can do regular old elementary school math, but you just have to deal with having only 2 symbols instead of 10 symbols. It's onerous, but this is how the computer holds numbers. Floating points, I drew a handy graph for a previous class when I was trying to hustle through things. So floating points have very big or can hold very big and very small numbers, and technically 0, but there's like some area between the very small number and 0 where it starts losing precision, and past a certain big number, it also loses precision. And oh, floating points are I can't even really call them weird or alien. It's just a floating point has an assumed mathematical statement going on as the way it's held in memory. A floating point number is I was saying, by the way, you all have the textbook, I assume, right? Okay, so the yep, it doesn't do this calculation every time. It is laid out with this calculation in mind. So I mean, I better starting with the simplest things. Bit number 31 is whether it is negative or not. If actually I can have a nice, useful, very fun demonstration of what the bejesus is actually happening. So a float with an assumed 32 bits is, again, to go back to this, the first bit is whether it's negative or not. The 30th through 23rd bits are the, I guess you call it exponent. Like if there's no bits on, it's assumed to be negative 126, so to speak. But in actuality, it's reserved as 0 when there's nothing on. To actually get negative 126, you'd have to say have 1 bit on. If you wanted to get 1 to the power of 1, if you wanted to store it as 1 to the power of 1, you'd have to use the most significant bit, because like the text says, it is assumed that whatever is stored here minus 127. So 128 is the only actual stored thing. It's just calculated to have minus 127 after that. Let's see. And if you wanted to get 1, you'd have to flip on all the bits except the most significant one, because that would boost it up to another 128. Also, fun fact, if you have all the bits on, instead of maxing it out, or instead of saying 1 to the 128, instead it says, throws up a 10, says infinity. I think that's actually mentioned in the book down here as I guess not. Oh yes. There's something of like, you can have positive and negative infinity and 0, and there were like 3 or 4 special cases for how a float holds bytes of one's positive infinity, one's negative infinity, one is just 0, because you want to be able to hold 0. And then there's like negative 0 or something to that equation, or to that effect, where it's not a redundant 0, it's treated as not a number or an error code. So going back to 1, the other thing is this mantissa, or as it's put in the book, fraction. So 1.f. So like this whole thing, or like the book says, this is functionally a math equation to start with. So if this is 2 to the 0th to get 1, and right now it's 1.0. Each one of these bits is an increasingly smaller fraction. So or technically it'd be 1 over 2 to that power, or like this is, or this is 1 plus 1/2. This would be 1 plus 1/4, 1 plus 1/8, and so on and so on down. So turns out very large exponent times very, well, the more things you turn on here, the more the closer it arrives to 2. Oh, yeah. See there's the not a number error, but you can still get very, very large numbers. And because the fractions being added become so teeny tiny, that means you can manipulate the number to become very large, very, very large and negative. Throw in error. We're very small. Let me check something. Could I do this by hand? Well, yes, but I don't think I want to. Gee. Yeah, so what was it? So because because a float is a number that's essentially just here's an exponent, it is in fact more difficult to add 2 floats together than it is to multiply them. Would anybody like to guess why? I give you a hint. It's to do with, well, it's made out of things multiplied by each other. If you have more than, oh, no, it's simpler than that, I think. So if you have 2 to the 8th times 2 to the 4th, or even 5 to the 8th times 5 to the 4th, how do you get the answer, or how do you calculate that? Or how do you calculate, yeah. Because the multiplying isn't really multiplying, it's just adding 2 exponents together. But like, oh, let's cower it out really hard. 2 squared plus 2 to the first. It has nothing to do with the exponents. You have to go and break it down into 4 plus 2. Then you have to do that. And that's 6, which is not equal to 2 to the 3 or 2 to the 2.5. And the other thing would be, and the other part of the float, the 1 point f, which can be just, again, 1 plus 2 to the -1, or actually, yeah, that would be yeah. So to again explain things, that 1/2 is 2 to the -1. 1/4 is 2 to the -2, 2 to the -3. So it is again kind of like the adding two exponents together thing, except they're negative numbers instead of positive. So all you have to do for, what was it? Actually, I'm not quite sure about that one because it'd be like 1.5 times 1.25 being the same as 2 to the -1 times 2 to the -2. However, if you got rid of the ones, because technically the whole thing is, or all of those bits are just the fractions added to a 1, and I was a little incorrect insofar as like it's not 1.5 times 1 or 1.25. It's that. So one 2 to the -1 times 2 to the -2. It'd be half time. Actually, what the heck am I doing? I have this. 1.25, meaning becomes that. So it's a kind of reverse of the, it's not quite the counting upward, or it's not quite this but backwards, but it's close insofar as like big number, that big number, run out of space, go this one, then do this one, then run out of space, then do this one, then this one, and so on and so forth. It's not quite that, because obviously you can see this go from number go down to number go up, but it's not the opposite, but it's kind of similar, I guess. So let's see. I already mentioned about the edge weird cases. with the infinite and negative infinite. You can't actually calculate anything using those, but you can use them as a comparison for very large numbers. Because if you want to, what's the biggest number I can get that's not infinity? Or my thing is going to start up from very small numbers. What can I compare it to, or what can I give the starting smallest value as? I'll give it start as negative infinity, so whatever it finds first is larger than negative infinity, so I can use that instead of picking some arbitrary number, because eventually someday that arbitrary number is going to actually be encountered. Let's see. Yeah, here it gives some we can try these for ourselves, as a matter of fact. To find the floating, whatever it is, for negative 7.75 to the 10th. We go with German sign, negative, then convert it to binary. Negative 111.11. So this part would be 7, and this would be the 0.75. Then normalize the scientific notation. So to turn that into scientific notation, it's, well, you move the decimal over 2. So that's 2 to the second. Because again, binary instead of decimal. Compute the biased exponent. 2 plus 127. And convert to binary. So converted to binary, there's that. So you can kind of think of it as this 0.1 being whatever the is assumed. The 0.1 is assumed by the mantissa. The 1111 here are the bits that will actually be used in the mantissa. Let's see, does that match what we have? Yep, it looks like it matches what we have in the book. And again, you can split this up into hex values for easier reading and storage, which is another trick of I'm reasonably certain I don't need to tell you that the only difference between a binary number and a hex number is the number of characters it takes to convey that information. It's kind of the same way with decimal. Or trying to really drive home the thing for anybody who is struggling with wrapping their heads around decimal, if anybody's left, is the values are the same between these things. The values between these things are all the same value. They just use different symbols and different numbers of them to get there. So is anybody, if I left anybody in the dust or otherwise confused things? I think I've hit most everything as far as the numbers go. The professor did cover other things in his earlier class. Characters and strings, how to number. I guess nobody has any questions, or speak now or forever hold your peace, because I'm gonna go get a drink and then come back in a second to help with any questions you have about the homework, and probably also look at the recording of the previous class. I think the professor touched on some other topics. So now I count 13. I don't know if that's because of them dropping the call or me dropping the call. I'm going to go get a drink of water, then I'll be back and help with labs if people need help. Otherwise, I will be back and then like look at the recording of the professor's earlier class to try and like summarize whatever other topics he included there. Down to 12. Oh yeah. Uh, did you did you check in the class Discord? Darn. It appears whoever did the recording for the earlier class didn't upload it yet.
Oh wait, last class like on Tuesday, right?
Oh no, I meant the teacher has two sections today, and he was here for the first one. I'm sure he was a bit late getting started on that one because he had to wait for the previous class to get out of the classroom. So the class started slightly late. He ran a little long and then handed it off to me to do to explain binary uh, and the binary math. And I mean, I guess I could try to do float calculations by hand, but floats are more a thing that is designed for the computer to use easily rather than designed for human usage. Um, he covered some technically related topics earlier in the first class today, but it was things like I think it was more to do with here's the physical being of the computer, and here's why we have uh, and here's why we have binary. Um, and the reason hexadecimal exists is it's not really it's not a separate language or representation. It's just easier for humans to read than it's easier for humans to look at a like 5 pairs of 2 letters instead of 5 pairs of what was it, like 2 1 or 4 ones? Yeah. If one letter is 4 ones and zeros, then it's much easier to see. Or EFAD is a much easier read than that. These still matter. Those letters mean the same thing as those ones and zeros, but they're much more information dense and easier for humans to read than a whole screen full of ones and zeros. Heck, I could say even if I broke that up by what letter is what number, then the hex like hex doesn't exist in the computer's mind. It's just condensing 4 binary digits into 1 digit, kind of like just changing binary to decimal, but it's an easier conversion because base 16 has the same root as base 2. Like you can just multiply it upwards and it condenses easier. Like decimal 10 is like that. There's, like you can see, there's kind of wasted area, or you have 2 whole digits you didn't use. So the hexadecimal thing is it doesn't leave unused space, I guess. Again, also, this is the part of the class where, hey, if you got questions on the lab or practices or anything like that, go ahead and jump in at any time. We're down to 10. Oh, thanks for jogging my memory. The exam is going to have, what do you say, conceptual things and practical, or like a conceptual section and a practical section. where the practical thing would be like a very short like a code snippet of assembly to do a specific thing, or like right. Oh, is it going to give a base 10 number and we have to convert to base 2 or 8? I don't think base 8 is going to come up. Or I think he didn't mention base 8 at all. I think he just mentioned hexadecimal and binary and decimal. And that was center. That was all you'd need to worry about. I don't know that you're going to have to do any actual math as such with binary and hexadecimal things. No, that's not quite true. You might be asked, add or subtract these binary numbers together, or find the 2's complement of this number, i.e. here's the positive number, find the negative number. This also works in reverse, by the way. Let's see. Sue. Oh, let's go with a byte and -4. So then you take the 1's complement of this thing, just flip all the bits. Then you add 1. And hey presto, it works forwards and backwards with flip the bits and add 1. And as mentioned, flip the bits. Add 1. Carry the 1. 0 again. Carry the 1. 1. 1. And so on. And hey, look, it's the -4 again. Will that come up in the test? No idea. That might come up in the like conceptual thing of like flip all the bits, then add 1. It works both ways. Do not try to flip all the bits and subtract 1. That will get you a wrong answer. I don't actually know off the top of my head when your first midterm is going to be. Hmm. I do remember he'd said that the format is going to be broken up into conceptual questions and practical questions. And yeah, assembly is interesting to me as well, insofar as it's very, very finicky, but that's because we've had 40, 50 years to optimize the bejesus out of it. And like, things that do assembly code and old programming languages are all like very low level stuff. Like if you have vulnerabilities at like kernel level or like operating system or below, then you're in big trouble, because that's really hard to get at. So it has to be free of exploits and very fast. And you want it very fast because it does those things a bazillion times a second. So, I mean, there there are jobs for people programming how processors work below the point of where the operating system touches them. Um, you can make bank with that because it is very, you know, it's delicate work, I want to say. Not many one there. Well, I'm technically always on the Discord, but I may not be paying attention. Um, I kind of want to say you're stressing out too much, or at least like, so you're aware of the practice things. Um, or he has given out practice assignments. Or like, let's see, subjects. Samples, tools, documents, library. Right. I only have access to the class website, not the student website, so I can't like look at those. But the practice things are going to be, quote, very similar, unquote, to the exam stuff. And given that, I believe he said if you're remote, then it's all open. It's all open book, open note. You can reference those examples, and they might be very similar to what is on the exam, such that you could just like take the stuff from the example and copy it to the exam, and it might only need slight changes to be a perfect fit. But I don't have access to those, so I can't help directly. But hey, if you guys got specific questions about examples or whatever, that's what I'm here for. Excuse me. I can't access the thingamabob for the is float, but on the class, the yeah class site, x86 programming library software is float. I can't see what it is, but that looks like something related to checking if the input is a float.